Good morning. This is part 1 of module 4. Therapeutic equipments. 6 of them are included in the module. This session is on the first two among them, the cardiac pacemakers and cardiac defibrillators. Cardiac pacemaker. The rhythmic beating of the heart is due to the triggering pulses that originate in an area of specialized tissue in the right atrium of the heart. This area is known as the sinoatrial node, which is known as the natural pacemaker. In abnormal situations, if this natural pacemaker ceases to function or becomes unreliable, or if the triggering pulse does not reach the heart muscle because of blocking by the damaged tissues, the natural and normal synchronization of the heart action gets disturbed. When monitored, this manifests itself through a decrease in the heart rate and changes in the electrocardiogram waveform. Any change in the normal sinus rhythm is called arrhythmia. During an arrhythmia, the heart can beat too fast, too slowly, or with an irregular rhythm. When a heart beats too fast, the condition is called tachycardia, and when a heart beats too slowly, the condition is called bradycardia. By giving external electrical stimulation impulses to the heart muscle, it is possible to regulate the heart rate. These impulses are given by an electronic instrument called a pacemaker. So a cardiac pacemaker is a medical device that generates electrical impulses which are delivered by electrodes to the heart, causing the heart muscle chambers to contract and therefore pump blood. It can be defined as a computerized device that regulates the timing and sequence of our heartbeat. A pacemaker basically consists of two parts: an electronic unit which generates stimulating impulses of controlled rate and amplitude, known as pulse generator, and the lead which carries the electrical pulses from the pulse generator to the heart. The impulse forming circuit determines the frequency and duration of the impulses. This is usually a multi-vibrator circuit with adjustable rate and fixed pulse width. The output circuit determines the shape and amplitude of the impulse. In almost all cases, the waveforms used for pacing are round-top rectangular pulses of 1 to 3 milliseconds duration with rates adjustable from 50 to 150 pulses per minute. The electrode arrangements for use with the cardiac pacemakers can be in the form of bipolar or unipolar system. In the bipolar system, 2 electrodes are placed on the heart for myocardial stimulation, whereas in the unipolar system, 1 electrode is placed on the heart and the other electrode is positioned elsewhere in the body. The classification of pacemakers into different types is based on the mode of application of the stimulating pulses to the heart. Based on the placement of electrodes, we have external, internal, and implanted pacemakers. External pacemakers are employed to restart the normal rhythm of the heart in cases of cardiac standstill, in situations where short-term or temporary pacing is considered adequate, while the patient is in the intensive care unit or is awaiting implantation of a permanent or an internal pacemaker. The pacing impulse is applied through metal electrodes placed on the surface of the body. Electrode gel is used for better contact and to avoid burning of the skin underneath. An external pacemaker may apply up to 80 mA pulses through 50 cm² electrode on the chest. This procedure is painful and is therefore used only in an emergency or a temporary situation. The external pacemaker is the one that has the power source outside the body. The pulse generators are usually battery powered. They can be worn in the pocket or strapped to a limb or to the torso. They are designed to function in the asynchronous and synchronous modes. Some units also operate in a synchronous triggered mode. The disadvantage of external pacing is that the electrodes eventually tend to burn the skin and the electrical pulses become painful. Also, each impulse causes an uncomfortable contraction of the thoracic muscles around the area of the electrodes. Internal pacemakers are used in cases requiring long-term pacing because of permanent damage that prevents normal self-triggering of the heart. The stimulating pulses can be preferably applied to a heart through a pacing catheter, passing through a vein and connected to the heart. The pacing current required is much less than when it is applied through the chest. And the voltage output of internal pacemakers is about 0 to 15 volt and available output current ranges from 1 to 20 milliamperes. Implantable pacemaker along with the electrodes is designed to be entirely implanted beneath the skin. The pacemaker components combine with the body tissue to form a complete circuit. The components are implantable miniaturized pulse generator powered by small batteries which can supply sufficient power for a long time. Output leads or wires connected directly to the heart muscle deliver impulses from the pulse generator to the heart and also senses the cardiac depolarization. During pacing, the impulse begins in the pulse generator and flows through the lead and cathode, stimulates the heart and returns to the anode. The pacing system can be unipolar or bipolar. The implantable circuit should possess certain basic requirements like highly reliable circuits, long lifetime for the power source, covering the circuit with biologically inert material so that the implant is not rejected by the body, etc. Based on the mode of delivery of pulses, we have asynchronous or fixed rate pacing and synchronous or demand mode pacing. In fixed rate pacing, the heart is stimulated at a continuous preset rate independent of its intrinsic electrical activity. The major disadvantage is that competition between the paced beats and the patient's intrinsic rhythm may occur, potentiating ventricular tachycardia and fibrillation. The demand pacemaker avoids competitive beating by sensing the electrical signals from the chamber it is pacing. Demand pacing is either inhibited or triggered. The block diagram of pacemaker is shown in figure. The pulse generator has two functions, pacing and sensing. Sensing is accomplished by picking up the ECG signal. In the case of dual chamber pacing, the P wave is also sensed. Once the ECG signal enters the sensing circuit, it is passed through a QRS bandpass filter. This filter is designed to pass signal components in the frequency range of 5 to 100 Hz with a center frequency of 30 Hz. This is followed by an amplifier and threshold detector which is designed to operate with a detection sensitivity of 1 to 2 millivolt. Sensitivity of this order ensures a reliable detection of cardiac signals sensed on the electrodes which typically have amplitudes in the range 1 to 30 millivolt depending on the electrode surface area and sensing circuit loading impedance. A refractory period T1 is necessarily incorporated to limit the pulse delivery rate, particularly in the presence of electromagnetic interference. It is meant to prevent multiple re-triggering of the astable multivibrator following a sensed or paced contraction. The free-running multivibrator provides a fixed rate mode with an interval of T2 via the output driver circuit. The output pulses of a length T3, synchronous with input signals that fall outside the sensing refractory period T1, are thus delivered at the stimulating electrodes. Based on the type of output waveform, there are three types of pacemakers. These are voltage pacemakers, current pacemakers, and current limited voltage pacemakers. Voltage pacemakers are those in which the current in the circuit is determined by the available voltage during the entire duration of the impulse. In current pacemakers, throughout the impulse, the current in the circuit is determined by the internal resistance of the pacemaker. And in current limited voltage pacemakers, it is primarily a voltage circuit, but the maximum current in the circuit is limited, preventing too large a current impulse to circulate when there is a low resistance in the electrode circuit. The three types of pacemakers are single chamber, dual chamber, and biventricular pacemakers. In a single chamber system, only one pacing lead is placed into a chamber of the heart, either the atrium or the ventricle. In dual chamber pacemaker, wires are placed in two chambers of the heart. One lead paces the atrium and one paces the ventricle. In biventricular pacemaker, leads are placed in both right atrium and right ventricle and the left ventricle. It synchronizes all the chambers and it is used in patients with severe heart failure. The next therapeutic equipment is cardiac defibrillator. Ventricular fibrillation is a serious cardiac emergency resulting from asynchronous contraction of the heart muscles. This uncoordinated movement of the ventricle walls of the heart may result from coronary occlusion, from electric shock, or from abnormalities of body chemistry. Because of this irregular contraction of the muscle fibers, the ventricles simply quiver rather than pumping the blood effectively. This results in a steep fall of cardiac output and can prove fatal if adequate steps are not taken promptly. In fibrillation, the main problem is that the heart muscle fibers are continuously stimulated by the adjacent cells so that there is no synchronized succession of events that follow the heart action. Therefore, there is an irregular rapid heart rhythm. Although mechanical methods for defibrillating patients have been tried over the years, the most successful method of defibrillation is the application of an electric shock to the area of the heart. This sudden surge across the heart causes all muscle fibers to contract simultaneously. Possibly, the fibers may then respond to normal physiological pacemaking pulses. The instrument for administering this shock is called a defibrillator. The bottom figure shows how the normal rhythm in fibrillating heart is restored by direct current shock across the chest wall. Therefore, defibrillation is a process in which an electronic device sends an electric shock to the heart to stop an extremely rapid, irregular heartbeat and restore the normal heart rhythm. The shock can be delivered to the heart by means of electrodes placed on the chest of the patient, which is external defibrillation, or the electrodes may be held directly against the heart when the chest is open, which is internal defibrillation. Higher voltages are required for external defibrillation than for internal defibrillation. DC defibrillation is more successful than the AC method in correcting ventricular fibrillation, but can also be used for correcting atrial fibrillation and other type of arrhythmias. The basic circuit diagram of a DC defibrillator is shown in the figure. In almost all present-day transthoracic defibrillators, an energy storage capacitor is charged at a relatively slow rate from the AC line by means of a step-up transformer and rectifier arrangement, or from a battery and a DC to DC converter arrangement. During transthoracic defibrillation, the energy stored in the capacitor is then delivered at a relatively rapid rate to the chest of the subject. A variable auto transformer T1 forms the primary of a high voltage transformer T2. The output voltage of the transformer is rectified by a diode rectifier and is connected to a vacuum type high voltage changeover switch. In position A, the switch is connected to one end of the capacitor. In this position, the capacitor charges to a voltage set by the positioning of the auto transformer. When the shock is to be delivered to the patient, a foot switch or a push button mounted on the handle of the electrode is operated. The high voltage switch changes over to position B and the capacitor is discharged across the heart through the electrodes. In a defibrillator, an enormous voltage of approximately 4000 volt is initially applied to the patient. Although short duration pulses can affect defibrillation, the high current required impairs the contractility of the ventricles. This is overcome by inserting a current limiting inductor in series with a patient circuit. The disadvantage of using an inductor is that any practical inductor will have its own resistance and dissipates part of the energy during the discharge process. The shape of the waveform that appears across electrodes will depend upon the value of the capacitor and inductor used in the circuit. A typical discharge pulse of the defibrillator is shown in the figure, which is called a Lown waveform. This waveform is more or less of an oscillatory character with both positive and negative portions. The discharge resistance which the patient represents for defibrillating pulse may be regarded as purely ohmic resistance. The most common waveform utilized in the RLC circuit employs an underdamped response with a damping factor less than unity. The electrodes for external defibrillation are usually metal disc about 3 to 5 centimeters in diameter and are attached to highly insulated handles. Most of the conventional electrode systems are circular, a little concave with sharp rims and an insulated backside. For internal defibrillation, when the chest is open, large spoon-shaped electrodes are used. Usually, large currents are required in external defibrillation to produce uniform and simultaneous contraction of the heart muscle fibers. The external electrodes contain safety switches inside the housings and capacitors discharged only when the electrodes are making a good and firm contact with the chest of the patient. This precludes the possibility of an accidental shock to the operator and risk of burns to the patient. Automatic or advisory external defibrillators or AEDs are capable of accurately analyzing the ECG and making reliable shock decisions. They are designed to detect ventricular fibrillation with sensitivity and specificity comparable to that of well-trained paramedics, then deliver or recommend an appropriate high-energy defibrillating shock. AEDs require self-adhesive electrodes instead of handheld paddles for two reasons. Firstly, the ECG signal acquired from self-adhesive electrodes usually contains less noise and has higher quality. Hence, it allows a faster and more accurate analysis of the ECG and therefore facilitates better shock decisions. Secondly, hands-off defibrillation is a safer procedure for the operator, especially if the operator has little or no training. The figure shows a typical automatic external defibrillator. The defibrillator accurately assesses the patient's heart by sensing electrical signals from the patient's heart via electrodes and using a computerized algorithm to interpret the electrical signals. The algorithm used in the modern defibrillators looks at 4 key indicators to determine whether a rhythm is shockable or non-shockable. These 4 indicators are heart rate, conduction, which is the flow of electrical waves through the heart indicated by the width of R wave, stability, which is the repeatability of QRS complexes, and amplitude, which is the magnitude of the heart's electrical activity. The block diagram of an automatic external defibrillator is shown. The ECG monitor monitors the electrical signals from the heart, and if defibrillation is required, the charge stored in the capacitor is delivered to the patient. The use of automatic implantable defibrillators is recommended for patients who are at high risk for ventricular fibrillation. An implantable defibrillator is continuously monitoring a patient's heart rhythm. If the device detects fibrillation, the capacitors within the device are charged up to 750 volts. The capacitors are then discharged into the heart, which mostly represents a resistive load of 50 watts, and to bring the heart into normal rhythm. This may require delivery of more than one high-energy pulse. Implantable defibrillator systems have 3 main system components: the defibrillator itself, the lead system, and the programmer, recorder or monitor. The AID houses the power source, sensing, defibrillation, pacing, and telemetric communication system. The lead system provides physical and electrical connection between the defibrillator and the heart tissue. The modern implantable defibrillators make use of a single lead with the multiple electrodes inserted into the right ventricle for ventricular pacing and defibrillation. The programmer, recorder, monitor communicates with the implanted AID and allows the physician to view status information and modify the function of the device as needed. The PRM is an external device that provides a bidirectional communication link to an implanted AID. This telemetry link is established from a coil which is contained within the vent of the PRM to a coil which is contained within the implanted device. This telemetry channel may be used to retrieve real-time and stored intracardiac ECG, therapy history, battery status, and other information pertaining to device function. The vast majority of cardiac arrest patients suffer from tachyarrhythmias which generally develop into ventricular fibrillation. However, a small percentage of cardiac arrest victims suffer from extreme bradyarrhythmias which require pacing. Therefore, most manual defibrillators currently in the market offer both demand and asynchronous external pacing facility. Block diagram of an implantable defibrillator with high output pacing function after defibrillation is shown in figure. It is composed of 5 battery powered units, sensing circuit, high voltage converter, switching circuit, defibrillation control circuit, and pacing control circuit. The heartbeat signal, which is detected by a catheter type heartbeat sensor, is amplified for heartbeat monitoring. The absence of a heartbeat for 3.5 seconds causes the fibrillation detecting circuit to deliver the turn-on signal, which then switches on the high voltage converter. At a predetermined voltage level, the thyristor switch allows the capacitor to discharge its current through the right ventricular electrode. After defibrillation, high output demand pacing is activated by using the residual energy in the output capacitor. The pacing rate and pulse width are controlled by the pacing control circuit, and the heartbeat signal is used for demand function. The figure shows the pacer cardioverter defibrillator. Thank you.